All right. Welcome everybody to today's stream. We're going to be getting started in looks like just over a minute. Let me share with you the link to today's whiteboard. I'll copy that and I'm just going to paste that into the chat notes. Again, this is just the whiteboard space I'll be drawing on today. So if you need to click back through something or if you want to access the link that's here in this post-it note, I think you can double click on it and get it open here. If not, I'll be pasting that link in the chat as well. This is our weekly live stream for PHYS 413 Quantum Mechanics for Jacksonville University Spring 2020. I do see we've got 8 folks viewing, and there are 5 students in the class, so I'm glad we've got some guests with us. Before we get into the quantum mechanics, I do want to confirm that yes, JU is finishing its spring semester online, so we will not be meeting in person again for this class. We will be finishing out the semester online, which is fine. I've already gone ahead and made plans for that. If you are taking summer classes, please be sure to just keep an eye on how long campus will be closed, because as of right now, summer classes will be starting online as well. One of the things I want to show you later is a Jupyter Notebook. Jupyter Notebook is an environment for running Python codes. It can do a lot more than we can do in our standard Trinket and GlowScript environments. So what I'm going to do is in the chat, I'm going to send you a link to our class, to a file in our class folder that has this Jupyter Notebook file. It's just called sphericalharmonics.ipynb. If you have Jupyter Notebooks, I'd encourage you to go ahead and open Jupyter and open this file. Download and open this file. If you don't have Jupyter, now's a good time to install what's called the Anaconda programming environment, which houses Jupyter. It's the best way to run Jupyter Notebook is through Anaconda. You can do that in the background if you would like during this live stream. If not, you can just make a note for yourself to do that in a little while, because I do recommend opening this. It's not required for class because I didn't teach you how to use Jupyter Notebook before we went online, but it is helpful. It'll be incredibly helpful in a few minutes when we need to visualize some 3D stuff. So today what we're going to do is we're going to talk about angular momentum. So we've got... Goodness, my screen is not writing well today. There we go. I was writing too fast. There we go. Angular momentum. So I'd like for you to do in the chat... go ahead and type out one thing you remember about angular momentum from classical mechanics. So that could be your introductory classical mechanics class. It could be an upper level classical mechanics class. What is one thing you remember about angular momentum? Let us know in the chat. And I have good news. I think I've figured out how to address the lag issues. Apparently YouTube has different latency settings for its streams, so now I'm only about 10 seconds ahead of you as opposed to a minute, so that is good. So let's see. Alyssa is asking, do you think I could use it in CoCalc? What is CoCalc? But sure, probably, exclamation mark. So let's just take a minute and put in the chat window, what's one thing you remember about angular momentum from classical mechanics? Could be an equation for it. It could be a generic description of what it is. It could be, I remember being confused about angular momentum. That's okay. Emily is posing the question, does inertia have something to do with it? Yes, they are related. Alyssa is asking about centripetal force. Yeah, it's related to that. We tend to stay away from forces in classical mechanics, but Yes. Oh, and Peter is chiming in with an equation, and I'm probably going to mispronounce his name. I'm sorry. Prakriti is saying it's a conserved quantity. Okay, so that's all wonderful information. So let's just go down the line. So the simplest way to think of angular momentum, right? So when you have linear momentum, it's an object's mass times its velocity, right? It's the moviness of an object, right? It's how fast it's traveling and how much stuff is traveling. Well, linear momentum is when you are moving in a linear direction, right? So your velocity is moving in a linear direction. Angular momentum is what you get when you are rotating around, and we use the symbol capital L. I'm not entirely sure why. You get to a point where the letters don't really make any sense. And basically, you turn linear momentum into angular momentum. You turn mass into the moment of inertia. Thank you, Emily, for that reminder. And you turn linear velocity into angular velocity. So you might remember omega is your number of radians per second as you spin around. Alyssa's correct. It is related to an extension of force called torque, because if you want to change the angular momentum with respect to time, if you want to have a change in angular momentum, you've got to apply a torque, right? And so if your torque is 0, then your angular momentum is conserved, right? And we really, really like conserved quantities in physics, because conserved quantity means it's constant. It means it's something that you can take as fixed throughout the problem. Conserved quantities are also important, we're going to see, in quantum mechanics, because when you have a conserved quantity in quantum mechanics, it means you can use it to label a quantum state. And then Peter is reminding us of how you define angular momentum. It's the thing's position crossed with its momentum. And we're going to see this is going to be where we start with angular momentum in quantum mechanics. So let's take a look at how we do this. So you might remember you have a cross product. So we've got R cross P. So R here is just the position vector, P is the momentum vector. What that means is that angular momentum has to be a vector. And so we need to have 3 components for it, right? So I need to have Lx equal to, let's see, that's going to be y momentum in the z direction minus z momentum in the y direction. Remember, when you take a cross product, you're doing everything either in alphabetical order, x, y, z, or you're doing in reverse alphabetical order, z, y, x. And when you do it in reverse alphabetical order, you get a minus sign. So that means Ly is going to be zpx minus xpz. You just flip each term around, right? And so that'll give you that'll give you the term that has the minus sign. And then Lz is going to be xpy minus ypx. And I know everybody has their favorite way to do cross products. The determinant method seems to be really popular among today's students. This is going to be important to us because, remember, in quantum mechanics, these momentum values are not numerical values anymore. They are operators. You might remember before we went on break, we had this equation that momentum was equal to h bar over I, derivative with respect to x. And so it's not a number, it's an operator. It's saying take a derivative and multiply by h bar over I. So whenever you have momentum acting on psi, the wave function, you're actually changing the wave function using this derivative. Now we're in 3 dimensions, so I need this to be the momentum's x component, and then I need the momentum's y component to be the same thing, but now we're going to take a derivative with respect to y. That is a very sloppy delta y. There we go. And I need my z component to be h bar over I d by dz. And so when you have this angular momentum stuff, wherever you have these p's, you're actually plugging in a derivative. So you're actually making an operator where you say where you say take a derivative and then multiply by this value. So for example, to do Lx, you're saying in this right-hand term here, you're saying take a derivative with respect to y and then multiply by z. And here you're saying take a derivative with respect to z and multiply by y. So it's kind of taking this notion of the operator to another level, because now in addition to taking a derivative, you're also multiplying. Now the good news is you're always taking a derivative with respect to one variable and multiplying by a different variable. So these are allowed to move back and forth. Normally you can't move the position and momentum around, but here you're allowed to, because taking a derivative with respect to z doesn't impact y, right? These are partial derivatives because x, y, and z are all independent variables. So anyway, these are our quantum mechanical angular momentum operators. This is kind of the starting point for talking about angular momentum. This is, if you have our class textbook, which is Quantum Mechanics by David McIntyre, if you've got that with you, you can find this construction at the beginning of section 7.3. In the regular edition, that's page 210. I know the international edition is a little bit off from that, but that's the beginning of section 7.3 labeled angular momentum. Okay. And it's interesting because this Lx, Ly, and Lz, these work, at least in terms of the way they function, they work very similar to our spin operators. You remember at the very beginning of the semester, when we were first learning quantum mechanics, we had spin operators, right? We had spin in the x direction, we had spin in the y direction, and we had spin in the z direction, right? And we had our spin states, right? So take a minute and in the chat window, tell me one thing you remember about these spin operators, Sx, Sy, and Sz, or about their quantum mechanical states, or anything about spin that you remember from the beginning of the semester. Feel free to dig through your notes. Take about a minute. Tell me one thing you remember about spin. All right, so Alyssa tells me z is up and down. That is the usual way that we set up our axes at this level. X is in and out, y is left and right. X cross y gives z. Yep, that's a right-handed coordinate system. That is one way to do it. Another way to think about that is z is usually the special direction. So usually if you have a magnetic field turned on, we usually say the magnetic field is going along the z-axis because that makes the spherical coordinates a lot easier to work with. Emily tells me everything can be written in terms of z up and down, right? Yes, so you might remember that, I think I still have enough room on here. So Emily's reminding us that the z you have as up and down. And then so for example, your positive state in the x direction can be written as a linear combination of the two. You take that, divide it by square root of 2. And then the only thing that changes is if you want this to be negative in the x direction, this becomes a minus sign. If you want it to be positive, negative in y direction, then one of these picks up an I. So yes. So we were working with these in bracket notation. Because that makes it hides a lot of the messy math with the column vectors and row vectors and everything. It makes that a lot easier to just work straightforward with. Yes, and Alyssa is reminding us that any psi you can write as a linear combination of up and down. So you only really need one of these, right? You only really need the SZ, and then you can write all the others in terms of that. Well, guess what? The angular momentum operators work exactly the same way. All you need is one of them. You just need LZ, and then you can write the states for LX and LY in terms of the LZ state. So let's take a look at what these states look like. So you might remember we had this. I have learned that I can change the background to dots, and then I can better keep my handwriting level. Yes, and Alyssa has brought up the uncertainty principle. You cannot measure the spin of one thing and then measure something else and then get the same value for the spin, right? So as long as you're measuring one spin value, you sort of mess up all the other spin values. Well, the angular momentum stuff works exactly the same way, right? So you might remember we had this stuff where if you act with SZ on your up state, you're going to get h bar over 2 times the up state. And then same thing with the down. If you act with xz on the down state, you're going to get negative h bar over 2 on the down state. Well, these angular momentum operators work very similarly. So let me draw a little squiggle line here to say we're working with different states. The angular momentum states are labeled in terms of two numbers. They're labeled in terms of L and M. Some of your textbooks will call this M sub L. So M might be replaced with M sub L. I find it's just easier to call it M, but I think your textbook labels it as M sub L. Basically what this is, L here is the total angular momentum. And then M is the angular momentum in the z direction. So for example, if I act on this thing with LZ, right, it has the exact same effect that acting on SZ plus does. It's going to spit out an eigenvalue. It's going to spit out M times H bar, and then it's going to leave me the same state LM. Another vertical bar there. There we go. So in other words, M is the label for the eigenvalue, just like 1/2 was the label for the eigenvalue up here, right? Because this was when you had a spin 1/2 system, right? So like, for example, an electron can have a spin up or a spin down, and your eigenvalues are h bar over 2 and negative h bar over 2. In this case, your eigenvalues are M times h bar, right? Because angular momentum, h bar, Planck's constant, has units of angular momentum. And so all of your angular momentum eigenvalues are going to have an h bar attached to them. So anytime you see an h bar, just think of that as an angular momentum. And so your state is going to have an eigenvalue of M times h bar. The reason this L is here is because M can be anywhere from, let me make sure I get this right, negative L to negative L plus 1 to negative L plus 2, etc., all the way up to L minus 1 and L. Right? So if your L, for example, is 1, let's say you're working with a total angular momentum of 1, your M can be negative 1, 0, or 1. Right? If you're working with an L of 2, then M can be negative 2, negative 1, 0, 1, 2. So it's also kind of like the harmonic oscillator in that you could think about this sort of ladder system where you're going up the ladder in terms of L. And your L can be any non-negative integer. So it can be 0, 1, 2, 3. Again, kind of similar to your energy level N in the harmonic oscillator, which is why the harmonic oscillator is so useful, because that same type of structure is showing up here. Excuse me. So you've got this eigenstate of LZ, the angular momentum in the z direction. It's always going to spit out an mh bar, and M can be any one of these numbers between negative L and L. L is just a measure of how much total angular momentum you have. Alyssa is asking, is this like an amplitude? Yes, you can think of L as being your amplitude. In fact, the reason we have this L is because we have another operator, right? Angular momentum is a vector, right? So vectors have components, but vectors also have a magnitude. So if you take the angular momentum vector and square it, right, this would just be Lx squared plus Ly squared plus Lz squared. This thing is also an operator, and it turns out this thing also has an eigenstate of Lm. If you act on Lm with this L squared, the magnitude of the angular momentum, it spits out another eigenvalue. It spits out L times L plus 1 times h bar squared, acting on the same state Lm. So these states are really neat because they're eigenstates of both L squared and Lz. Let me get this other one up here, mh bar, Lm. So in other words, this state here, this Lm, right, this is the same Lm on both left-hand sides and the same Lm on both right-hand sides. These are both eigenstates of L squared and Lz at the same time. So all that stuff we had to worry about where you couldn't measure Sx and Sy and Sz at the same time, that is still true for the components, but you can measure Lz and L squared at the same time, because what we're going to see in a second is L squared and Lz commute, right? So this thing is called the commutator. Anytime you put two operators in brackets like this, you're saying give me L squared Lz minus LZ L squared, right? If these were just numbers, this would always equal 0, right? A commutator is a thing that is trivial with numbers. It doesn't make any sense to talk about a commutator with numbers, but with operators or matrices or derivatives like we have here, it does make sense to talk about a commutator because if two operators commute, meaning if L squared LZ and LZ L squared are the same thing, then they can have the same eigenstate, right? Lx, Ly, and Lz cannot have the same eigenstates, right? An eigenstate of Lx can never be an eigenstate of Ly and Lz, etc. But L squared can share eigenstates with Lx, Ly, and Lz because they all have the same fixed L amplitude here. All right, let me take, we are 20 minutes in, so let me take a hydration break, give you all a chance to post any questions before we take a look at what these things look like. While we're waiting for questions, let me give you one other little piece of information. This is the commutator for L squared and LZ. You can also show that the components have a really neat commutation relation. If you take commutator of Lx with Ly, so if you take Lx Ly minus Ly Lx, you get IH bar times Lz. So you go xy gives you z. Similarly, if you take Ly Lz commutator, you get IH bar Lx. And there's one more pair you can do, Lz with Lx. Anybody want to guess? Anybody want to guess what it gives you? I bet you can guess. IH bar Ly. So it's really cool because these things, they're cyclically related, right? You can go x, y, z. Here you go, y, z, x. Here you go, z, x, y. Right? So there's other fancy ways to write these. If you label them as 1, 2, 3, you can actually use the famous Levi-Civita symbol to yes, Alyssa has guessed. Excellent. You can actually use the Levi-Civita symbol to relate these because you can just call them L. Wait a minute. Yeah, LLLM can equal epsilon LM in IH bar LN. It's actually really cool. This is I can't remember. I think there might be an assignment question that asks you to use these or something. But this is something you can prove pretty straightforward if you just go back to their derivative definitions, right? The derivative definitions here. You can actually prove that with just a couple of lines. Okay, let me double check over my notes here, see if there's anything else we need to talk about before we look at what these things look like. Oh yeah, I should also mention these things are important. These angular momentum states are important because these are going to be essential when we get to the hydrogen atom. Because when we go to study the hydrogen atom, right, the basis of chemistry, our gift as physicists to the field of chemistry, this is the basis of chemistry because in a hydrogen atom, you have a proton, you have an electron flying around. The electron is orbiting with a conserved angular momentum. Since angular momentum is conserved, it means the hydrogen wave function is just these angular momentum wave function times a radial wave function. So you can separate r, theta, and phi. And this part takes care of the angular part. It takes care of theta and phi. We just have to figure out the radial part. So you're going to see this again next week when we get to the hydrogen atom. Okay, so let's get to the question of what do these things look like. I'm going to send you a link. I'm also going to put it up here, but I'm going to send you a link about what these things look like in terms of wave functions, right? Because it's nice to be able to have these commutation relations. It's nice to get the eigenvalues, etc. But we want to get an idea of what these things look like. It turns out these functions, these LMs, they are what we call spherical harmonics. You can think of spherical harmonics as being like the 3D version of the sine and cosines. There's a lot of math up here at the beginning. This is all important stuff. But here's the definition of the spherical harmonic. There is the mother of all normalization factors out in front. So this is just to make sure the thing normalizes to 1. There's a thing called the associated Legendre polynomial. It's basically a polynomial built out of cosines. And then there's an e to the im phi, right? So you can see here you've got your L and M. So the L and M here, these are exactly the same L and M that we had before. So all this L and M stuff in the eigenvalues, that's also showing up here in the spherical harmonics. Let me blow up my screen for just a second. There we go. So these are the same L and M that show up in the eigenvalues. This is how they show up in the wave function. So the Legendre polynomial gets determined by L and M. That just determines the order of the polynomial. And then e to the im phi, that's what gives it its wiggliness, right? This is the thing that makes them complex, right? So you know by now that e to the I something is wiggling in the real and complex planes. You also know that when we take the modulus of this thing, this piece will go away. We'll just be left with this thing. And they have some neat properties. You can split them up into real and imaginary parts. There's some neat little recursion relations, things like that you can set up. They are really fun to integrate, but what I want to get to is what do they look like, right? What do these look like in space? This is what they look like. So remember, these things are labeled in terms of L and M. L is on the bottom, M is on the top. M has to be less than or equal to L in terms of magnitude. And you notice they're only showing you the positive M's because M only makes a difference over here, whether it's positive and negative, in the e to the im phi. And since we're taking the modulus, this piece goes away. So the M plus or minus, positive or minus negative M doesn't really make a difference there. So this is what they look like. So 0, 0 is a sphere. It's just a uniform distribution. You say, okay, that makes sense, right? You should always start with something simple. Here's the next sort of excited state. So this is with a total angular momentum of 1 and an angular momentum z value of either 0 or +1 or -1. And you notice they look different, right? 1 is shaped kind of like this dumbbell thing, and 1 is shaped like this apple thing where you've got this, this core kind of falling in the middle. Then you get up one more step complicated. You've got L equals 2, and you've got M either 0, +or -1, or +or -2. And they get a little more nuanced, right? So you get a triple dumbbell or cheeseburger looking thing there. You get this neat little chalice looking shape, and then you get another apple looking shape. Then you move up to L equals 3, and we get an Oreo over here. We get a, take a mod. Prakriti's asking, we take a mod to keep only the real part of simplification. Okay, so she's asking, why are we taking the modulus? Modulus is going to equal the real part squared plus imaginary part squared, so that we can visualize it. We can also take just real or just imaginary part. And actually the code we're going to go to in a second will allow you to adjust that in any way that you want. So like for example here they show you the real part and the imaginary part. So remember these are the modulises. And so that's what it looks like kind of when it comes to, you know, squaring the wave function to get the probability. This is to show you what the function quote unquote actually looks like. So here's the real part on this side. Here's the imaginary part on this side. You can tell they always look similar to each other. They're just rotated, right? That's what e to the I something does, is it gives you a real part and imaginary part that are just rotated compared to each other. So like for example, here you've got the little sandwich going this way. Here you've got the sandwich going this way, right? It's not they're not all that different. They just get rotated basically. And anyway, that's nice of Wolfram Alpha to show us those images. Plural moduli, thank you. Now tell me what the plural of hypotenuse is. I've been wondering about that one for a decade. This is what the first several of them look like in terms of functions. They're really no different than functions you've seen before. They're just going in 2 dimensions, right? So you know what sine and cosine and EDI phi look like. The difference is now we've just got a function of a trig function of theta and a trig function of phi mashed together in spherical coordinates. So these are really just the sine and cosine extended to spherical coordinates. And all the numbers out here, they're simply normalization constants, right? So everything is just sines, cosines kind of thrown together. It's just a question of what combination you throw them together is. Hypotenuses, okay, I'm quoting you on that from now on. You can also write them in terms of Cartesian coordinates. I have never done that. I don't see the need to do that. I don't understand why that's on this page. So anyway, these things are really neat and they're fun to play with. You can do a lot of neat mathematical things with them, but it's kind of difficult to just work with the equation. So what I'm going to send you in chat is a link to a Jupyter Notebook file. If you've got Jupyter Notebook, go ahead and open this. If not, take about 20 minutes this afternoon, install Anaconda, open up Jupyter, open up this file and play around with it. So this program is based on this link here, where I was able to find Spherical Harmonics already programmed out. Basically what you do is you set the values of of L and M, and it will graph for you the modulus of Y. So remember, YLM is a spherical harmonic with eigenvalues L and M. It's a function of theta and phi, and it's going to graph these for us. It's going to graph them a little bit differently. It's going to use a color scheme. So for example, this is 1, -1. This is what that looks like. So let's go back over here to remind ourselves what that looks like on Wolfram Alpha. So 1, -1, it's the same thing as 1, 1 in terms of the modulus. It's this little apple-shaped thing, so it goes out far in the middle, and then it caves in at the top and bottom. Well, same thing over here. You've got it a higher value on the outside and a lower value at the top and the bottom. The only difference is this one is showing it to you in terms of color instead of the dumbbell setup, right? So instead of showing you all of these kinds of things, it's going to show you basically a heat map across the sphere. Because these are nice diagrams, but it's kind of artificial because there's nothing actually reaching out that far. It's really just showing you, it's using the distance from the origin as a sign of the value or the amplitude. So let's take a look at how this thing works. First, we import a lot of libraries. It takes a lot to put together the spherical harmonics. Most importantly, though, we're importing from SciPy. This is Scientific Python. They have the spherical harmonics built in. I spent about a week last semester trying to make my own code to build spherical harmonics. Lo and behold, they were just a Google search away. So this SPH_HARM is here to get you the spherical harmonics right away without having to type up all of this stuff. So it's basically pulling these from a library or a recursion relation or something like that. Then we have to set up a grid of spherical coordinates. So spherical coordinates usually come in r, phi, and theta. We're not really interested in the r. We're interested in theta and phi. And so remember, whenever you go around spherical coordinates, one of them has to go from 0 to pi. One of them has to go from 0 to 2 pi. Otherwise, you end up double counting the sphere. That's just a little pro tip that they mentioned in math class, and I feel the need to repeat over and over again for students. And basically what we're doing, we're setting up a grid of that. Now, it's not a grid like you usually think about it. It's not like an X and Y grid. It's more like a latitude and longitude grid. So you can think of it as being like a globe. We're going to convert those into Cartesian coordinates because we need those in order for the computer to work. So I guess you do need to have these in Cartesian coordinates. I am mistaken. But we're using the usual relationships there where z is coming down, or phi is coming down along the z-axis, and then theta is going around the xy plane. Yeah, that's flipped compared to the way we usually do it in physics, but it doesn't really matter, right? It's just a name. And then this line 19, this is the piece that you change. You really don't need to change anything about this code other than L and M here. Let's say, for example, we want to start with the simplest one. Let's go 0, 0. And as a reminder, M must be less than or equal to L. In terms of amplitude. There we go. And this is a neat trick I learned recently in Python. You can say variable comma variable equals number comma number and set them together. I don't know. I think that's cool. I don't think it saves you any computer time, but it is neat to look at. And then what we're going to do is we're going to calculate the spherical harmonic, normalize it. And so it's using that function here, spherical harmonic of M comma L, theta comma phi. That's it. That's the call to the spherical harmonics. Everything else is just dressing. Everything else is just getting the thing onto a graph. and it's going to create a color plot here of our spherical harmonic. Let's see what we get for 0, 0. So as a reminder, this thing should be uniform. It should be uniform across here. And now that I've got my streaming software running, this is going to take longer than it did yesterday when I was trying this out. Excuse me. All right, there we go. That just took a second. It's complaining because I'm putting in a 0, but it's graphing it anyway. And so it's graphing for me a nice uniform sphere, just like we have over here, because we start out with y0, 0 is a constant. It doesn't have any trig functions attached to it, so that's nice. Let's go up one step in complexity. Let's try L equals 1, M equals 0. That should not give me the divide by 0 error that I was getting before. Let's see, this one should be this little dumbbell looking thing here. And lo and behold, that's what I get. I get red on the top, red on the bottom, blue in the middle. So red indicates a higher value. So I'm getting inflated up toward the top. Red down here gives me a higher value. I'm getting inflated down here toward the bottom, but I'm caving in the middle. Let's take a look at one more. Let's see, how complicated do we want to go with this? Let's go 3, 2. So let's try L is 3, M equal to 2. Oh, look at that. So we get this nice little thing inflating out here, and then it caves in the top. So this graph is the same thing as this graph. It's just this one is showing you contours. This one is showing you a heat map, right? Now, let's see. We had folks asking about whether we're looking at the modulus or the real part. You can actually change that over here. So instead of using absolute value, what we can do... oops, there we go. What we can do is get rid of the absolute value here. And I believe we just say dot real. Does that need parentheses? Let me remind myself. This is the page where I originally got this from. They were showing the real part instead. Okay, no parentheses required. So you can instead look at the real part or the imaginary part. And so this is a look at the real part of this function. You can see it's different, right? Because if I were to look at imaginary instead, it's going to look similar, but these are going to be flipped around. You see where I had a red before, I now have a blue, or I have a blue, I now have a red. And that's just because real and imaginary parts on a wave function, they're just rotated compared to each other, right? You've seen that by now, that they have the same general shape. They're just rotated by 90 degrees, 45 degrees? I guess it's 45 degrees. Yeah. Or 90 degrees, excuse me. Yeah. So you can look at the amplitude or the real part and the imaginary part, and you can go as high with this as you want, right? Whereas Wolfram Alpha, only takes you to so many iterations. With this code, you can go to any value of L and M that you want to look at, which is pretty cool. Oh yeah, let's confirm that going to negative m is the same as m. So let's change this -4 into a 4. You'll see we'll get the same distribution for our modulus. Not so if you go real part versus imaginary part, right? So if I just look at the imaginary part, let's say, right, I get this structure. And now let's change our m to a -4. Right, so I've got a red in front here. So my cursor is pointing at something red right now. Now it's pointing at something blue, right? So m is going to flip the phase around like that. So if you wanted to, you could play around with this. I haven't played around too much with this graphing method. I would love to be able to get to rotate this around, but right now that's the view that we have of that. Let's see. Yeah. So that's the only way in which the negative m makes a difference. So I want to take a few seconds to pose any questions before we get to we got a few minutes at the end to wrap up. So I want to see if there are any questions, and then we'll do a couple of activities to wrap up. Like I mentioned earlier, these spherical harmonics and this L and M stuff comes in handy when we study the hydrogen atom. So you might already know from your chemistry class that your hydrogen atom, its wave functions, they look a lot like these things, right? Because your hydrogen atom is going to get labeled in terms of an energy level N, an angular momentum magnitude L, and angular momentum Z component M, or ML usually. And so this is the stuff that ends up labeling your energy level or your state in your chemistry class, right? So in chemistry class, you draw all these little electron energy levels, right? And so when you go up here, you're increasing N. And then when you go along this way, you're changing L and M, right? Does the angular momentum change the energy level? It's been a while since I looked at that. No, it is just N. Okay. Yeah. It is just N. Okay. That's right. So anyway, yeah, so all these energy diagrams that you drew in your chemistry class, that was really quantum mechanics you were doing, because you were working with energy levels, angular momentum, and M. So all these, we call these things the quantum numbers. Right? So the eigenvalues are these things put into formulas. So like L times L plus 1 times h bar squared, M times h bar, 1 over n squared times 13.6 electron volts, I think, something like that. So this is the actual eigenvalues. But these are what we call quantum numbers, right? Because they are the numbers you use to label the state. It's kind of like this is the minimum information you need to specify what state an electron is in. And so when you're working with a computer code, quantum numbers are great because these becomes your labels for all of your states, which is amazing. And so eventually you just start talking about the NLM instead of worrying about what they actually are. Yes, Prakriti has pointed out the same thing. Yes, these are quantum numbers, exactly. I want to take a look at two other things before we break for the day. I'll post this link in the chat as well. I made the comment earlier that when you move along this angular momentum stuff, it's like moving up and down in the harmonic oscillator, right? Where we have these raising and lowering operators. It turns out you can get raising and lowering operators for angular momentum as well. I'm not going to go through the derivation. In fact, it's not even in the chapter for this week, so this is just bonus information. But here's the commutator relations that we saw earlier for Lx and for any two of the components. It turns out you can also define a raising L and a lowering L that will take you up and down in terms of your M value. So you just define them as a linear combination of Lx and Ly. The plus is Lx plus ILy. The minus is Lx minus ILy. So you can raise or lower just by applying this combination. It turns out what happens, and this is why I didn't want to write this down because I hate having to remember this thing, but if you apply L plus to a spherical harmonic, you get the next highest spherical harmonic. Or if you apply L minus to a spherical harmonic, you get the next lowest spherical harmonic. So this L plus or minus on YLM gives you YL of M plus or minus. Now, this thing has to terminate, right? Because you can't go, for M, you can't go any higher than L or any lower than negative L. And so that's what this piece is here for. This piece is here to cut it off if you ever try to get above the maximum or below the minimum. This thing in the square root will end up giving you 0, right? Because if you plug in an M equal to L when you are raising, right, you'll have L times L plus 1, and then here you'll have L times L plus 1 subtracted. Same thing if you're trying to lower beyond the minimum. You've got L times L plus 1 minus negative L times negative L minus 1. Those two cancel again. And so it's this neat little contraption that lets you go up and down in terms of M. It lets you change your Z component while keeping your L value the same and not allowing you to go beyond the top or the bottom. So anyway, that's really neat. You may see that in a graduate level course, or it may come up in our hydrogen atom chapter. I don't know yet. But that is a really neat little construction. It's worth knowing that that exists, even if you don't, even if you're like me and you never get around to memorizing what's underneath the square root here. Okay, I want to take a couple minutes at the end here to refer you to a video I've posted for the final project. So remember, in this class we have weekly assignments and we have 3 projects. I've combined the last few assignments into one, but there is one more project for us to do. Let me bring that up here. And that is, it's here in our class folder. I'll open that and then put that into the chat. Project 3, there we go. So this is due on April 20th. So you have just under a month to finish this. This should be a pretty straightforward thing to do that shouldn't require too much technical work, I don't think. Your goal is to study the behavior of a wave function and a potential energy that cannot be solved, right? So when we get to the end of this class, we will have gone through nearly all the exactly solvable problems in quantum mechanics. If you want to study something beyond this semester, you have to use a computational tool. There's an infinite number of potentials out there that we can't solve for. So what I've done is sent you a little video that will go over how we study unsolvable potential energies. There's no technical secret or anything. It's just a video of me saying, hey, here are some examples of unsolvable potential energies. Let's use our code. For the project, I'm asking you to choose one of these potential energy functions. So there's the Morse potential, which is used for atomic interactions, the Lennard-Jones potential, also used for interatomic interactions, and two-body electric repulsion. So this is just Coulomb's law with 2 different repulsive poles. I'm asking you to use the range 0 less than x less than 5 for each of them because you can't really go over the asymptotes there. So we're just going to keep it between 0 and 5. And I'm asking you to set up this potential energy in our code. So our code over here on Trinket, there are a few things you need to change. Let's take a look at the shopping list here of what you'll need to change. Here we go. I would like to get the instructions up here, the code. There we go. And let's up the font size. So the things you'll want to change on this is the potential energy function. That's this V of x. You have changed that a couple times now, so you have an idea of how to do that. You're just going to change this V of x to match your selected potential. You can use any one of these 3 potentials. So I should have put V equals in front of this. So we'll say V equals. I will get that techified in just a minute when we get offline. So you're going to set your potential energy equal to one of these. It doesn't have to be a piecewise function, right? These are nice functions, except for the asymptotes. I'm also asking you to adjust x min and x max. So that is a little bit farther down, I think. Yeah, starting in line 73 here. X min and x max, I'm asking you to make this from 0 to 5, just so that we've got a nice window there. And then I'm asking you to set up an initial wave function that you think will look interesting. I am not going to tell you what wave function to use. Up here in psi real or psi imaginary 0, you set this to be whatever interests you. You could use a coherent state. You could use a sine and cosine. You could use an eigenstate of the harmonic oscillator. You use what you think would be interesting to watch. Because the thing is, if it ends up behaving funny, that's either something worth studying or you can just go back and change it, right? And then I'm just asking you to discuss a few things. Discuss how the wave function evolves under the influence of this potential energy. Discuss how the wave function behavior makes sense based on your experiences. And I have makes sense in quotation marks because, as we said on the first day, quantum mechanics doesn't make sense to people. But how does it match up with your previous experiences of how wave functions behave? And discuss how it's unique compared to other experiences in this course. Each one of these has something unique in the behavior of the wave function. I'm asking you to just talk about, what makes it different. What makes it different than the harmonic oscillator? What makes it different than the infinite square well? It could be as simple as it makes different ripples, or it has a different number of maxes and mins show up, or something like that, right? This is not a master's thesis, right? This is simply you telling me what you observe about something that looks interesting, right? And that's it. That's the third project. That is the last major chunk of the course grade, is changing a potential energy, changing a range, and changing an initial wave function, and watch it and tell me what it looks like. As you've seen, this code runs slow depending on your computer, so you may want to pop yourself some popcorn and just have yourself a movie night. If you even want to set up a Zoom meeting or something for you all to, or Google Hangout for you all to watch your wave functions evolve together, you can do that. That's becoming the thing now, is for people to watch movies at the same time, watch the same movie at the same time in their homes remotely. The project will be graded based on you completing this, right? So I can't tell you that your observations were wrong because you're the one making the observations, right? So I'm grading it based on, did you complete all 7 of these items. Let me go back over to my notes here. So that's all that I have in my notes for today. Next week, we will take a look at Chapter 8, the hydrogen atom. So if you are so inclined as to read ahead to Chapter 8, about hydrogen atom, it's exciting. That's a neat way to end a quantum mechanics class, because the hydrogen atom is kind of our crowning achievement. It's our gift to chemistry. With time permitting, the week after that, I would like to talk a little bit about some basics of solid-state physics. That is not in the assignments. It is not a required topic, but it's my area of expertise, and this is a class where that intersects with, so I'd love to get to talk with you about that a little bit after we cover the hydrogen atom. So with that said, I want to thank you all for your time. I'm scheduled to be on for another 10 minutes. I'd be happy to take any further questions in the chat. Otherwise, just as a reminder, I'll have office hours on Google Hangouts this Friday at noon. I'll send you a link to that shortly before it begins. So for the sake of the video, I'll say thank you all so much for your time, and I hope you have a safe and healthy week. All right, I see.